Hey everybody! So welcome to our last lesson in Unit 1, which is all on accuracy and precision. Now, a lot of times people think that accuracy and precision mean the same exact thing, but in fact, their definitions are very different from one another. You can be accurate and not precise. You could be precise but not accurate. You could be neither precise nor accurate, or you could be both. And as chemists and as scientists, it's really important to know in an experiment if you are accurate and or precise. And other than just knowing the definitions, there are a few calculations that we can do in order to quantitatively determine if you are accurate or precise in the lab. So we are going to talk about the difference between accuracy and precision and how to calculate accuracy and precision. Let's go ahead and do the notes. So accuracy and precision, what's the difference between them? Accuracy is the closeness of measurements to the correct or the accepted value. If you are doing something and you get a value that is what you're supposed to get, that means that you were accurate in your measurement. Let's say you're trying to find the density of aluminum in the lab. And the real density of aluminum, I believe, is 2.7 grams per milliliter. And if you were doing the lab and you got, let's say, 2.6 grams per milliliter, you could say you're pretty darn accurate. You got an answer that's close to what you should have gotten. If instead you got a density of, let's say, 7.4 grams per milliliter, you would not be accurate because the density that you obtained in your experiment is very different from the one that you were supposed to get, the real value or the accepted value, what you would find in a textbook, let's say. So that's accuracy, it's getting the right answer. Precision, on the other hand, you don't have to get the correct answer, but precision is getting the same answer over and over and over again. Now, one of the big ideas in science, part of the nature of science and what it is your information that you test for has to be repeatable. You can't just do a lab once, or you can't just try to find the cure for cancer once and say, I did it, I found the cure for cancer, and then never do that again. Your experiment has to be repeated. And if you get the same answer repeated over and over again, that's precision. You have to get the same thing multiple times. So in the lab, a lot of times students get upset. They're like, oh, Mrs. Snyder, why do I have to do this 5 times? Well, you have to do it 5 times because you have to show that I am precise. I'm getting the same answer over and over again. It goes to show that you are doing everything exactly the same, because if your answers were all over the place, then you know that you're doing something wrong. So precision is getting the same answer over and over again. And the best way to kind of explain accuracy and precision is with darts. So here, this one on the left-hand side, if you're throwing darts and you get the bullseye every single time, like what this picture is showing, that means you're accurate. You might not be precise, but you're pretty darn accurate. Whereas over here on the left, all of these darts are all really close to each other. In fact, they're much closer than these darts are in the accurate depiction. These guys, you didn't get where you want to get. They didn't get the bullseye every time, so they're not accurate. But they were, in fact, very precise because they got in the same exact spot every single time. So here, notice this guy is accurate, not necessarily precise because we're all over the bullseye. Whereas this one on the right is very precise because all of these darts are very close to one another. And but you're not necessarily accurate because you didn't get where you want to get every time. In your notes, there's a couple of bullseyes. We're just going to take a second here and talk about what it means to be accurate and precise. So if you are both accurate and precise and you're throwing darts, right, you would get the bullseye every single time. And we mean dead center in the bullseye every time. Notice how here we have all of these darts that are pretty spot on to that center point, accurate and precise. If you're accurate but not precise, you're still going to get right around the bullseye every single time, but all of your darts are kind of far apart from one another. So notice here, most of them are in the bullseye, but you have some that are kind of outlying the perimeter. So you're getting where you want to get, but your answers aren't necessarily close to one another, or in this case, your darts aren't necessarily close to one another. Notice the difference between these two here, both accurate and precise, accurate but not precise. If you're precise but not accurate, that would look kind of like this bullseye, which is the one that I showed on the slide before. So all of your darts are very close to one another. Notice they're much closer than these ones are, because this is not precise, but this one is. However, you didn't get where you want to get. You can get in the same exact spot every single time, but you're not getting where you want to get. In your science or math classes, you'll see something like this, because if you do a problem and you get an answer, but the answer is wrong, you try it again and you get another wrong answer or the same wrong answer, and you try it again and then you get another wrong answer. You're very precise because you're solving it the same exact way every time, but it's not the right way to solve it. So precise but not accurate. Now, if you're like me and you throw darts, you're probably neither accurate nor precise. I mean, you get one in the bullseye and you get super confident, and then like you throw another one and the next one goes, you know, over to the upper left-hand side. You throw another one, it's on the floor. You throw another one, it's out the window, right? They're all over the place. So here, you're neither accurate nor precise. There's no rhyme or reason as to where the values are. If you were in a lab and your data looked like this, probably need to try something again. Now, those are qualitative descriptions of accuracy and precision. So again, they're more descriptive. However, in the lab and in chemistry in general, we like to quantify values. We like to have very exact numbers to represent how accurate are we or how precise are we. So the way to determine accuracy is by calculating a percent error. And your percent error, of course, calculates the accuracy of an individual value or an average of numerous values. Because again, you don't normally like to do something once, you like to do it a few times. By quantitatively comparing it with the correct or accepted value. So to determine if you are accurate or if you are correct in what your value is that you obtain in the lab, you would find the percent error. Basically, percent error tells you how wrong you are. So you really want a 0% error. You want to be 0% wrong in your lab or in your experiment. And there's a very easy calculation in order to find percent error. And percent error is equal to your experimental value minus your accepted value divided by the accepted value times 100. The experimental value is what you would have obtained in your experiment. So it's your value. If you were finding the density of aluminum and you got 7.4, that would be where you put 7.4. That's what you got, the experimental value. The accepted value would be whatever the real density for aluminum is. So that would be what you find in a textbook or on the internet, or what I would tell you the real density is. That's your accepted value. It's what it should definitely be. And of course, it's a percent, so we want to times that whole thing by 100. Let's do an example here together, sample problem 6. So sample problem 6, dealing with percent error. So before we get started, I'm just going to rewrite this equation down. So percent error is equal to, I'm going to abbreviate here, experimental value minus the accepted value divided by the accepted value times 100. So let's see what we have here. A student measures the mass and volume of a substance and calculates its density as 1.40. So that's what the student found. The correct or accepted value of the density is 1.40. what is the percent error of the student's measurements? So it says very matter-of-factly, the accepted value is given to us. And the accepted value is 1.30. So that's either given in a book or by the teacher or online, wherever. That's what the answer should be. When the student did this experiment, however, they got a different answer. And their density, they found, was 1.40. So again, that's the experimental value. The accepted is what you should have gotten. Let's just plug these values in to the percent error equation. So percent error is equal to the experimental value, which is 1.40, minus the accepted, 1.30, divided by that 1.30 again, times 100. I like to keep my units there. I think it's just good practice, but it's not wrong if you don't write the units. When you solve this, take it one step at a time. So do this top part first. So, of course, this is going to be 0.10 grams per milliliter divided by 1.30. I just think it's easier to keep things, don't do it all in one shot on the calculator, because if you do, calculator is going to do order of operations and you might get the wrong answer. And then after you divide and multiply by 100, you should get 7.7% error. Which is not too bad. That means that this particular student was about 8% wrong in their answer. So they're 7.7% wrong. In our chemistry lab, I like to say that if you are less than 10% error, that's considered good. So if you were to get a 7.7% error, that would be acceptable. Not that if you got more than that, you'd have to do the lab over again, but you should be able to figure out, what could have went wrong? Why did I get such a large error? What happened here? So this student is 7.7% wrong. Let's go ahead and look at how to quantitatively determine precision. So percent precision is the second way of quantitatively determining accuracy and precision in the lab. A couple more steps than finding the percent error. It's a little bit more complex, but it's definitely not hard. It just has more steps to it. This is kind of like an easy way of finding a standard deviation of a value, because we want to know how close our values are to one another. So if I have a set of measurements that I found in the lab, again, for the density of aluminum, I want to know quantitatively or numerically, how close are those values to one another, by what percent? And we could do that by finding the percent precision, which determines the closeness of the values in a set of quantitative measurements. Again, quantitative is always numerical. I love to say those words because I think they're really important, just in vocabulary in general. And the way we find this, the percent precision, is we take the mean absolute deviation divided by the mean of a set of values, and we're going to multiply that by 100. Again, because it's a percent, we have to multiply by 100. A couple more steps to this problem, but again, I'm going to walk you through all of the steps so that you see how to find the mean absolute deviation, and of course the mean, which hopefully you know the mean is a fancy way of saying the average for a set of numbers. Let's go ahead and do sample problem 7. And to use sample problem 7, I put together this really nice table. I usually set up some sort of an organized table when I'm doing all of these problems, but you don't necessarily have to do something this nice. But for this first one, I gave this to you so you can see kind of how to solve everything. Let's do sample problem 7. Sample problem 7. Now, I don't have the actual note packet here, which is why I wrote mine out, but I tried to make it look pretty darn similar as to what's in your notes. For future videos, I'll definitely have the notes in front of me so you can see kind of what I'm doing and how to write it down, but hopefully this works. So sample problem 7 says a student finds the density of a sample of zinc 4 times and obtains the values of 7.14, 7.08, 7.12, and 7.20. What's the percent precision? So we want to know how close are these values to one another. What I normally like to do is to set up at least some kind of a chart. Yours definitely doesn't have to be this, drawn out and this exact, but I'll show you kind of how I do it in one of the next problems. But I have trial numbers and I set them up here. And what I'm going to do is just going to write those densities that the problem gave me into this column here. So I have 7.14, I have 7.08, we have 7.12, and 7.20. The first thing we want to do with all 4 of these values is we want to find the mean. And remember, a mean is the fancy way of saying the average. So let's find the average for all 4 of these values here. We want to add all of these up and divide by 4 because there are 4 numbers. When you do that, make sure you keep your significant figures. So I'm going to have 3 sig figs in my mean. You should have 7.14. So that's the mean of all of those 4 values. That's the average. We want to find how far away is each individual density from the mean. And to do that, we're going to take each density, so in this case I'm going to use 7.14, and I'm going to subtract from that the mean, which is this number down here. And notice I have these absolute value bars. So whatever you get for an answer, if it's negative, you just want to make that number positive because all you want to know is how far away is each value from the mean. So for this one, and I'll write the workout here just so you can see it, but you don't have to write the workout. You can just write the number. The density here is 7.14, and I'm going to subtract from that the mean, and of course I get 0. You're subtracting here, so I'm going to keep my significant figures, and I know it's 0, but just so I know how many significant figures are technically in this number. Let's try this one. So I'm going to take 7.08 minus the mean, and in this case you get a negative value, so you get negative 0.06. But it's absolute value, the absolute deviation. So we're just going to make that a positive value. Try the next one. Again, you'll get another negative value, but you're just going to make it positive. And you get that value there. So this is how far away each individual density is from the mean itself. So it's the deviation. If you're deviating from something, you're going away from where you should be going. So this is how far away is each value from that. Now we want to find the mean absolute deviation. So we want to find the average of all 4 of these numbers. So let's find the average there. And when we do that, so we should have one significant figure in our answer. I'm going to round this guy to 0.04. So what this means is that, and I'll write this out here, this means that on average, the density is about 7.14 grams per milliliter, and most of our densities that we calculated lie within this range. So most of the densities that we found lie between 7.14 minus 0.04, which is 7.10, and 7.14 plus 7.14 plus 0.04. That means most of our measurements lie within this range. Now, if I notice here, these are kind of far apart from one another. So, of course, this one lies within that range, so does that one. These two are kind of like outliers, but they balance each other out because they're both on average this value here. We're not done with the problem yet though, but we have everything we need in order to solve this. So in order to find the percent precision, or how close these four values are to one another, we're going to take the mean, absolute, deviation, divided by the mean, times 100. A lot of times students like to call this the MAD divided by the mean. So let's take our mean absolute deviation, which is 0.04, divided by the mean, times 100. And you should get a value of, looks like my answer should have one significant figure since I'm dividing, 0.6% precision. So what does that mean? This means that our numbers are within 0.6% of one another, which is pretty darn good. I always tell my students, if you are within 5% precision, in our lab at least, that's considered good. So if you're below 5% precision in any lab that you do, you will say that you were precise in your measurements. So this student here, if this was the data they collected and they did all of this stuff right here, they would say, yes, I'm precise because I have a 0.6% precision, which means that all four of my values are within less than 1% of one another, which is very, very good. So now that we have those two mathematical approaches down, we can calculate the accuracy and precision of a set of data, or both, because a lot of times you'll need to do both for a lab. Let's do sample problem 1, or practice problem 1. A student experimentally measured the volume of liquid in a graduated cylinder and found it to be 10.4. So it looks like that's my experimental value, 10.4 milliliters. The teacher corrected them and said that the measurement is actually, so the accepted value, is 9.7 milliliters. What is the percent error? So in this case, it looks like we're finding the accuracy. So we're trying to find the accuracy here. How accurate was this student? Was this student correct? Yes or no? So let's plug it into our equation. Percent error is equal to the experimental value, which is 10.4, minus your accepted value, which is 9.7, divided by your accepted value again, times 100. And when you plug this in your calculator, you should get 7.2% error. Now, it's not, the question isn't asking this, but is this student accurate? We would say yes, because it's below 10%. Something else I should say is if you get a negative value, that's okay. The negative value just means that you got less than what you should have gotten. So if you would have a negative 7% error, that's still considered accurate because it's still only 10% away from what it should be. This student ended up with a higher value than they should have, so which is why the percent error is positive. If they got something like 9.4, it would be a negative percent error, but they're still pretty darn close because it's within 10%. So 2 says the experimental, all right, so right away it says experimental value. I usually like to take the questions and kind of write down what it's telling me as I'm reading it. I think that helps me solve problems, especially word problems like these. The experimental calculation of the specific heat of aluminum was found to be 0.156 calories per gram degree Celsius. In a chemistry textbook, the value, so it says chemistry textbook, so that has to be the accepted value, was determined to be 0.191 calories per grams degree Celsius. Is the student accurate? So again, we're trying to determine the accuracy here. So To determine if a student is accurate, we want to find the percent error. So that's what we're going to look for. Don't let these units confuse you, because as long as they're the same units, which, spoiler alert, they will always be the same units for you, you don't have to worry about what the units are. You just have to use the numbers and plug them into the equation. So percent error is equal to experimental value, calories per grams degrees Celsius, minus that accepted value, calories per gram degrees Celsius, and let's divide that by. Notice for this one, my experimental value is less than the accepted value, so you will get a negative percent error for this. And that's okay, because you can still be within 10%. When you solve this, you should get negative 18.3% error. Now, the question particularly is not asking for the percent error, but you need to find the percent error in order to answer the question. So although I boxed this one, you need to take this a step further, because it's asking, is the student accurate? And then explain. So let's look at this value. Is the student accurate? We have negative 18%. This student is 18% lower what they should have gotten. So here, we would say no, the student's not accurate, because the percent error is higher than 10%. Now again, even though it's negative, you're still more than 10% away. If you think of a number line like this, we have 0, we have 10, we have negative 10. If you're at negative 18 all the way out here, you're still more than 10% away. You're 18% away from 0. So no, the student is not accurate because their percent error is higher than 10%. So in order to properly answer this question, you do need this little blurb down here. You need this part in order to find that out. So make sure you're looking at the questions correctly and solving them appropriately. Number 3, a student measured the mass of an object 5 times and obtained results of those 5 values there. What's the percent precision? So here we want to know, are these values close to one another? What I like to do for this is, because I'm not given a chart, I kind of like to make my own chart. So what I'm going to do is just list these numbers going down. First things first, with those 5 values, let's find the mean of all of these. So let's find the average of those. When you do that, you should get 34.6 grams. So that's the mean. We're on our way to solving this. Now what we need to do is we need to find the mean absolute, or the absolute deviation from each of these values. So we need to find out how far away is the mean from each of these numbers here. So let's go ahead and do that. We'll find the absolute deviation. These are the measurements, say. And there's the absolute deviation. So let's take this value, 34.9, minus 34.6, and I get 0.3. 34.5 minus 34.6 gives me negative 0.1, but remember, it's absolute. So if it's negative, make it positive. Let's try the rest of those, going down. And you should get each of those absolute deviations from each mean, or from each measurement. Now let's find the mean of these absolute deviations. Let's find the MAD, the mean absolute deviation. So find the average of all 5 of those values, and you should get 0.7 grams. Didn't actually solve the problem yet. So, in order to find the percent precision, we need to, So percent precision is equal to the MAD divided by the mean times 100. The MAD is 0.7. The mean is 34.6 times 100. So when you divide these in values by one another, your answer should have one significant figure. You have about a 2% precision. Now the question is asking, is the student precise? Or it's asking, I'm sorry, what is the percent precision? So you would be good just leaving that. However, let's just take this a step further. Is the student precise? We would say yes, because our percent precision is below 5%, which is pretty darn good, which means these values are really close to one another, which is what you would want as a chemist. Sample problem 4. I'm going to kind of work this out on paper, but I'm going to write it down and then I'm going to explain to you what I did just to make this last one go a little bit faster. Here we go. First things first, I just listed all 3 of my densities down. And then I found the mean of all 3 of those values, and I have 7.43 grams per milliliter. Now we need to find the deviation of each density from the mean, just like we were doing before. And I get all of those deviations from each individual density. Find the mean of all 3 of the absolute deviations. So the MAD, or the mean absolute deviation, is 0.44. Set up my equation. So the percent precision is equal to the MAD divided by the mean times 100. And I get 5.9% precision. Question's not asking for a percent precision, it's asking for an explanation. Are these students precise? We're above 5% here. So we would say no, not precise, because the percent precision is above 5%. And again, for us, that's kind of just the rule of thumb that I go for. If you have a percent precision above 5%, your numbers aren't really that close. Which you could see just by looking at these. I mean, these numbers are really far away from one another. So this student was not precise. Second part it's asking is, are the students accurate? Well, let's think about it. It says that the students were asked to find the density of an unknown metal. So if it's an unknown metal, do you know what the accepted value is? No, it doesn't tell you what it is, and you can't even look it up because the metal is unknown. So the accuracy cannot be determined because the identity of the metal is unknown. You don't know what the accuracy is. You don't know if you're accurate or not in this example because you don't know what the metal is. So you can't look up the accepted value. You would have your experimental value, that's the mean right here. That's what you would find the average to be of the density. But you don't know what the accepted value is because it's not telling you what it is. I hope this helped. If you have any questions, let me know. Make some notes in your packet and ask me next time you see me. But we're going to do lots of practice